Previously, I had worked a lot on entanglement and equilibrium states of matter, in quantum ground states, in thermal states. But we got interested in not just the equilibrium physics of entanglement, but also how entanglement changes in time. Okay, and so I'm going to tell you a little bit about that story today, really about how information is sort of scrambled up and spread out across a complicated interacting quantum many-body system. Okay, and I emphasize this story is a ongoing story. We're just getting started exploring this physics. At the very end of the talk, I'll speak about the very first experiments that have probed or begun to probe some of this physics.
So quickly,
yes.
when you say non-equilibrium, then tensor network is not much use, or are you going to generalize this?
That's an excellent question for another talk. But the answer is naively, tensor networks are not useful because you make lots of entanglement. However, that entanglement is not physically observable. It's encoded in very complex many-body correlations. So for the purposes of many observables, you can actually remove that entanglement, and then tensor network becomes useful again.
Right, that's what they usually do.
Yeah, so, but that's another talk. Related to this, but not the same. Okay, so just to emphasize that this is a work in progress, here is a volume of Landau-Lifshitz from the future that we're hoping to write. So somewhere in this theory of entanglement, this is volume 12. It's also edible because they like mixed-use things in the future, I guess. So it's a work in progress. All right. So what is scrambling? So I thought the best way to tell you, instead of giving you a bunch of words, is just to show you what scrambling is using my patented quantum simulator, the S-Wave machine, which is me in a room with my computer using something called a Krylov method to evolve the quantum state. So what I'm going to do is I'm going to show you in a simple closed interacting many-body system of a few spins what scrambling is and why it's interesting. Okay. So the setting is I'm going to actually have a system consisting of 7 spins. And I'm going to evolve in time with some unitary dynamics. So it's all...
Brian, do you need to worry about whether it's integrable or not? I'm just trying to...
Yes, absolutely.
So you didn't say anything about that?
I will in a second, but we will specifically consider a non-integrable system.
I feel better about it.
In fact, here is the Hamiltonian I'll consider. Some of you may have heard the scrambling story before, but one thing you probably haven't seen is results on this particular Hamiltonian, which is something I've been working on for a while. This is a Hamiltonian which is, I'll call the parallel Ising model. And it consists of 3 terms. So one is an Ising-like SZ-SZ interaction with some kind of power law decaying amplitude. So the nearest neighbors have certain interaction, and then the further neighbors fall off in a certain power law fashion. With a power here 6, which is chosen out of a vague inspiration from experiments in Rydberg atoms, but we can change this parameter. There's also a longitudinal field, so a field in the z direction, and also a field in the x direction. And so if, for example, you took this Hamiltonian, you turned off this term and truncated this to the nearest neighbor, that would be an integrable model. I don't want that because I want to really we'll see that scrambling is associated with chaos, with quantum chaos. And so we want to have a non-integrable thermalizing Hamiltonian. So I turn on this term, and I also add these next neighbor interactions. And I choose these parameters. So the nearest neighbor interaction is of order is 1. The z field is half, and the x field is also about 1. Okay, so it's sort of generic Hamiltonian. And so in order to show you what scrambling is, I'm going to consider a sort of slightly funny setup. I want to basically track how information moves and spreads in this many-body system. So the way I'll do that is I'll imagine I have some information which starts here on this first site. And the way I'll track that information is that I'll entangle it with a reference system, this little red dot, to which nothing ever happens. So this reference just sits there. It's just entangled with the system in some way. And basically, by following how this entanglement changes, moves around in this complicated system, I'll follow the way information spreads. Now, for the rest of the system, I want to start in, for simplicity, a maximally mixed state. So a very high temperature state. So this will access the entire spectrum. But for later use, I'm going to introduce something called the memory, which is actually maximally entangled with the rest of these states, these sites here. So that the whole system is in a pure state consisting of a bunch of Bell pairs. All right? So the first site's entangled with the reference. The next 6 sites are entangled with 6 sites of a memory. Okay. And so there will be 14 sites in all in this system. And this kind of definition or interpretation of scrambling goes back to what's called the Hayden-Preskill thought experiment. So essentially, I'm going to show you that experiment, that thought experiment, numerically here. And just to emphasize, the dynamics takes place only on the system variables, the black dots, the memory and the reference, nothing ever happens. And the diagnostic that I'll use is called the mutual information. So this is defined here. I'm going to calculate the mutual information between the reference, which is R, that's the red, with some collection X of the degrees of freedom here. And this mutual information is defined in terms of these entropies, as like that. And the important thing about this mutual information is that if the mutual information between R and some collection of degrees of freedom X is 1, or more precisely, if 1/2 the mutual information is 1, then that means that R is maximally entangled with that set of degrees of freedom. So in other words, if I have all the sites here, the mutual information between the reference and all the rest of the sites is 2, and that means that somehow this reference is maximally entangled with the rest here. Okay. So that's the probe. And so it's kind of obvious physically that it's obviously going to be entangled with all of the things in some collective way, because I can just reverse this time evolution, just de-apply this unitary, and then I exhibit that the entanglement is there on the first site. And so the interesting question is to ask how this entanglement spreads amongst the subsystems of this many-body system. Okay, so just to emphasize it, at time 0, if I have the reference here and I label the sites 1, 2, and so forth, the mutual information is just 1 when I'm at x equals 1, and it's 0 otherwise. And that's kind of physically obvious. These two are entangled. The rest are unentangled with the reference.
Ron, may I ask you a question?
Yes.
I mean, there are many interesting issues here. You are
Yes.
choosing one.
Yes.
I mean, if you take 10 of these spins and diagonalize it and look at time dependence,
Yes.
you can ask literally thousands of questions.
Yes.
I have asked about hundreds, so I know. So what is so particularly interesting about this reference and memory? I mean, it looks very artificial to me. If somebody does an experiment, one will not even see that. In fact, Chris Mondo does experiment on this system, right? So
Yes.
it's very superficial. Can you motivate why I should think about reference? I have all the information. I've diagonalized the system.
That's right. That's right. So this is what you'll see in just a second is that this is a very sharp way of characterizing how this information here spreads across the system.
More so than if I just look at the memory of the initial state, how it's decaying and so on.
That's right, because that's a global thing, right? That's sort of telling you how the initial state, the whole amplitude is decaying, right? And what you'll see in a second is actually that physics is totally factorized out here.
Yeah, but I can ask how the decay of memory at one site. I mean, once you have diagonalized, you can ask any question you want.
Yeah,
right?
good question, good question. So let's go a little further and ask that. So here I show you the mutual information between this reference and one site here. So this is like the memory of one site. This is like what you're asking about. And I plot it here for x equals 1, 2, 3 out to 7, right? And so you see at 0 time, the half mutual information is 1 here. That's because it's maximally entangled with the first site. Then it very quickly drops to 0, or to very close to 0. And you see, if you look at other sites, there's a little bit of a bump. It looks like something's kind of moving away. So that's nice intuition. The information is propagating away from the boundary. However, none of the mutual informations are very large. They're all quite small at late time. And now if you looked at other correlation functions, for example, spin-spin correlation function on a single site to test this memory effect, these will all also decay. And so out here, after say time 5, it looks like nothing's happening as far as this is concerned. The dynamics looks like you've reached thermal equilibrium. And in fact, we would say you've reached local thermal equilibrium. Nothing local is changing. But if we look at this non-local physics as encapsulated in these entanglement measures, then we can still see something. So now what is scrambling? Let's do the same thing now. Let's look at the mutual information between the reference and one site, but where we also allow ourselves access to this memory, which is entangled with the quantum state. Okay, so I'm just doing the same thing, but now I'm asking the mutual information between reference and one site plus the memory. Remember, nothing's happening to the memory. The memory is not evolving in time. It's just some fixed set of spins you have in your lab. But now you see something totally different. So the mutual information is plotted here as a function of the position x. I'm allowing the memory in every case. And you'll see, okay, if I look at the first site, the mutual information drops a little bit, but then recovers and asymptotes to some value a little bit above 0.6. But in fact, what's remarkable is that it does the same for all the other sites as well. So you see, remember, time 5 was where everything stopped happening. But now, after time 5, you still have dynamics. Something's turning on here. And this progression in x as a function of time is literally the spreading of this entanglement across the entire system. Right? That's what you're seeing here. And the memory, in this case, is a tool to illuminate this spreading. It's sort of giving you access to the information by letting you have essentially knowledge of the initial state as well. So it's saying if you know the initial state and you have access to one of these guys, then you can, in a sense, recover the entanglement. Okay, so this is the sort of surprise of scrambling. This is the first incarnation of scrambling.
So in this case, you consider your Hamiltonian is some local, generically non-equal Hamiltonian, right?
Yes, that's right. So for example, if you go back to this, if you had some sort of like particle hopping Hamiltonian where maybe the entanglement just hops around but doesn't become more complicated, then maybe what you would find is that there'd be like a bump here, and then a bump there, and then a bump there, and it might just sort of ballistically go, for example.
But the local in the non-equal is essential.
That's correct, yes.
So the relationship between the system and memory, the yellow lines.
Yes.
Were they initial conditions or were they?
That's right, they were the initial state. So as far as the system is concerned, it's a maximally mixed state. As far as the system plus reference plus memory, it's a bunch of bell pairs. So it's sort of the simplest kind of entanglement you could imagine.
Yeah, but similar things can be done without starting from maximally entangled state. You can do very similar things.
Yes, yes.
It depends on the initial condition, but maximally entangled is just one possibility.
That's right, that's right. In fact, you can see these same curves without any entanglements if you know what to look for. So I think it's hard to capture exactly how strange this is, but one thing to note is that the mutual information is the same for every site at late time. So that means the entanglement between the reference is contained in any site you want, right? It's not just in one particular site. It's spread over the entire system. And that's one of the essences of scrambling, is that it's spread everywhere. Yeah.
Is that value like universal, like the late time value?
No, it's not universal. What we can say is that if the system is scrambling, how many sites do you need to fully recover the information, fully recover the entanglement? And we know that what that number is the amount of the reference plus a little bit extra. And that little bit extra can be quantified in a precise way, which I won't talk about here. But to give you an example, suppose I had now 2 sites. You'll see it's much higher. It's close almost to 1. And so as a function of the, again, the position, every nearest neighbor combination of 2 sites plus the memory is almost maximally entangled with the reference. Okay, so these entanglement is kind of everywhere in the system at once. It's spread over all the sites, and it's not just in few body correlations, it's in many body correlations. And if you made this a little bit larger, even 3, it would get closer to 1 and so forth.
Is focusing about the mutual information between R and only the reference?
The reference or the memory? The mutual information between the reference and the memory. Yeah, that's always 0. Because they started unentangled. The unitary only acts on the system, which you trace out, so you can just remove it. So that's what's amazing. You take the reference, it's totally uncorrelated with the memory. You add 1 extra site in this complicated scrambled system, and suddenly they're maximally entangled, right? However, if you just had that 1 site in the memory, again, there's no entanglement. So it's something magical about the combination of these 2 things that gives you the physics. Okay. But to Shankar's point, can we access this time scale, the scrambling physics, without going to this system memory reference setup? And the answer is yes, or at least we know now yes. In the early days, we didn't. So let me show you how to do that. This is, again, the state of the system. I've gotten rid of the reference in the memory now. And again, it's evolving unitarily. So now I'll show you those curves again of 1/2 the mutual information between two sites in the memory, and then some mystery thing, which I put in black here. And you can see, for example, if you look on this line, the crossing between the black lines and the colored lines, it's sort of progressing in time uniformly. So it's measuring the same time scale. It's growing in the same way. But these black curves are something that are property just of the system. So what do you think these things are? Anybody want to guess? No guesses? Yes, they are these things that people have been talking about so much called out-of-time order correlators. So here's the definition of an out-of-time order correlator. Let's just think about unitary operators for simplicity. So I take two unitary operators, V and W. W sub t is the Heisenberg operator, defined here. And I form this funny correlation function where I start with my state, I apply V, then W at time t, then V dagger, then W at time t dagger. And then I compute the overlap with the initial state. And why is this called out of time order? Because if you sort of think about the way the time arguments go, you sort of start at time 0, go to time t, back to 0, and then back to t again. So this necessarily involves, in at least the naive way of thinking, it involves some kind of time reversal, where you're sort of taking the system forward in time, then backwards in time, then forward in time, then backwards in time again. And a nice physical interpretation of this object is that it measures the degree of non-commutativity in the system. So to be precise, if you look at this object, which I call C of t, which is called the squared commutator, it's the commutator of W at time t with operator V, absolute value, squared, expectation. And that's equal to 2 minus twice the real part of this thing. So in other words, when f is 1, V and W commute. And when f is close to 0, they don't commute. So if we go back to this picture now, what I'm showing here is out-of-time order correlators between the first site and some other site as a function of position. And you're seeing that as a function of position, the commutator is sort of turning on. Initially, all these things commute. That's everything being 1 up here at the initial time. And as a function of time, the operator at site 1, which is growing, the Heisenberg operator is going to getting bigger. It's encompassing more of the system. It's growing in time, and it's getting progressively fatter and fatter. It's taking up more of the spin chain. And so as I probe that commutator with operators further out, you see that non-commutativity turns on, then turns on, then turns on as I progress outward. So now it's sort of something more physical, I think. The commutator we know, from linear response theory, for example, is a measure of information propagation in a system. And so the one trick that I'm doing here is not looking at the average value of the commutator, which you would find would decay in these thermalizing systems, because you ping a system and the pinging goes away at late time, typically. Here I'm looking at the square. That gets rid of some of the phase factors that give you this 0 averaging out. And in that way, I'm able to access this interesting new scrambling timescale. Okay, this is just to say, I just want to flash this slide to point out that there's a nice paper by Pavan Hojer and company in which they make the correspondence between these mutual informations and out-of-time order correlators more precise for a certain quantity called the second Renyi mutual information. Not worry about the details of that, just so you're aware that this exists. Okay, it's not an accident that it happened in this model. It's a general feature. And actually, I'll make one more comment, which is kind of cute. The way to connect the memory plus system plus reference to the sort of isolated system is that you can always think about a time evolution operator, which has inputs and outputs, as a quantum state by taking these legs and bending them around. Sort of diagrammatically, you can view this matrix like a state on twice as many degrees of freedom. Okay, so that's a kind of fun theoretical trick. So now let me talk about one other aspect. I sort of talked about the late time physics of scrambling. Let me talk about the early time physics. So here now I plot for the same model on 14 sites now. So I'm looking at a bigger system. I've gone from 7 to 14 to make things nicer. I plot 1 minus the real part of f, so this is essentially that commutator. I take the log base 10 of it and I plot that on this axis. Okay, so down here this is just machine precision noise, so ignore that. But what you see from about time 2 to time 4 or 5 is that this thing grows by 10 orders of magnitude in an almost perfectly exponential fashion. So in other words, I could write this function f, the out-of-time autocorrelator, as 1 minus some very small number times the function which grows exponentially with time. And then, of course, there are corrections that take over once this thing becomes large. So what is this extended period of exponential growth signifying? What is the meaning of this? Well, this is where chaos enters the story. The idea, going actually all the way back to the old Russian literature, Larkin and Ovchinnikov, is that this out-of-time autocorrelator is actually essentially a probe of chaos in semi-classical systems. So imagine, for example, that the operator v was e to the I position, and the operator w was e to the I momentum. Then you can show very easily that the leading order term in this out-of-time autocorrelator at early time is just the average value of the commutator of q and p. However, we have the correspondence principle, which says this commutator can be related in some regime to IH bar times the classical Poisson bracket. And this Poisson bracket can be evaluated, which is just the time derivative of the final position with respect to the initial position. And that's the definition of the butterfly effect in classical chaos. I start my initial condition here, trajectory goes in some place. I change the initial condition a little bit, the trajectory goes in a completely different direction. And these trajectories diverge exponentially. So that's encapsulated here, some h bar times e to the lambda sub L t. So lambda sub L is the Lyapunov exponent of the classical system.
Brian?
Yes?
When you shift to the Poisson bracket, you're losing some quantum features, right?
That's right.
Even though you added the IH bar.
That's right.
So is it a quantum chaos or a classical base?
As I've presented it here, it's sort of like we're evaluating this at maybe early time using some classical chaos picture. But this data here, this is for a spin chain of 14 spin halves. There's no classical anything here.
Right.
This is fully quantum. And so what we like to do is propose that this kind of exponential growth is some kind of quantum version of a Lyapunov exponent. That's the proposal. Yes?
What is setting the time scale here? You're giving us a dimensionless time, but physically what goes into setting that time?
Yeah, great question. So in the spin chain, it's the separation between the operators. So if you're looking at the out-of-time autocorrelator between operator on site 1 and site x, the time that it takes for this thing to become significantly different from 1 would be of order x. And there would be a velocity defined by that, the ratio between the time and the distance, which will actually feature in a moment in this thing. Does that answer your question?
No, but I'll wait until.
Okay, sure.
Maybe you set the exchange coupling to 1, right?
That's right. That's right.
That defines the time limit.
Yeah, that's right. So I'm measuring units in the lattice spacing, and I'm measuring time in units of the exchange coupling, which is 1. Yeah.
Is there a rationale for considering exponentials, or is that what works?
That's a great question. In fact, I've sort of cheated. If you look at spin chains, take whatever spin chain you want, you'll never see this. It never looks exponential. Actually, this model is the only model I know of where you see this exponential growth.
Actually, I have to give up my credit. I was talking about the exponential on the next slide.
Oh.
Sorry.
Well, okay. I take it back, Jay. Not as smart as I thought, sorry. Yeah, so I just mentioned this is actually one area of inquiry right now that we're working very hard on, is to try to understand the early time growth.
I mean, the growth probably is non-universal. It doesn't have to be exponential, right? I mean, you can say that it will saturate somewhere. I mean, these are very complicated problems.
Yes.
I don't pretend to know the solution, but
it's not clear. At some point in time, a year or two ago, there was an expectation that everything would grow exponentially. That was chaotic. Now that seems to not be the case. There's still some exponential growth, but maybe there's other time dependence that makes it hard to extract. So maybe we just haven't gone to big enough systems yet to see this, but so it's complicated actually. Yeah, Jay.
Without some exponential, the motion of the Lyapunov exponent is.
That's right. That's right. We need this exponential growth to see the optimum. Yeah, and we need the separation of scales. We want to see many e-folds or many decades here.
I mean, if you look at simpler problems, pre-entanglement, after all the word entanglement entered our quantum were only around 2000. No quantum mechanics book had the word entanglement before that.
Unfortunately.
But we were talking about spin decoherence,
Yeah.
how quantum memory goes away and so on for a long time.
Yeah.
Since the 50s, when people did spin echoes. So there's a lot known about how a collection of
Yes.
spins in any dimension relaxes.
Yes.
And it's known exponential is just one of various possibilities. Okay?
Yeah.
And some of those problems you can solve exactly, assuming some distribution. So if this belief that it should all be exponential, what does it come from? What is the theoretical argument? I have not followed that.
Well, in fact, I mean, I would say it's just wrong. I mean, we definitely know models where it's not exponential. For example, if you take what's called a random circuit model, like imagine I have a Hamiltonian which is random and fluctuates in time. So this is like you think this is very scrambling, right? Because it's sort of changing constantly. We actually can solve exactly in that case the result for the growth, and it looks like diffusion with velocity. So it has a very different structure. So this is the picture, which I've belabored enough, so I'll move on. The butterfly flaps its wings, disturbs the wind pattern, and these operators V are like the velocity that measure it. Now, one fun twist to this story is, and actually where some of the interest in out-of-time order correlators arose in the recent literature, is that you can actually study these things in models of quantum gravity using the ADS-CFT correspondence, anti-de Sitter space conformal field theory correspondence. And you'll find that in Einstein gravity, you can compute this out-of-time order correlator or something similar to it. Really, this is calculation you're doing in the dual CFT, the sort of dual quantum field theory, but it has an interpretation in the gravity theory in terms of shock waves. And what you find is that it's 1 minus some exponential, which is 2 times pi times the temperature of the system, divided by the entropy of the black hole. And that's a very universal, that happens in any dimension for any size black hole. Right? And moreover, it was actually proven, or more or less proven, certainly at a physics level of rigor, that assuming you have this separation of timescale, so you have the possibility of many e-folds, or many decades of growth, then if you do have exponential growth, that exponent cannot be larger than 2 pi times the temperature. So actually black holes in ADS-CFT saturate this bound. And so people would say that they are the fastest scramblers in nature. But I emphasize this bound doesn't require any holographic stuff. It's just a property of quantum mechanics. It comes from analyticity in the complex time plane in the thermal state and from unitarity, essentially, and complex analysis. Okay. So that's my kind of longish introduction to give you some visceral sense of what scrambling is. So just to reiterate, it's essentially the mixing up or spreading out of information, which is initially simple or initially localized amongst all the degrees of freedom of a system. It's a phenomenon which is ubiquitous. It can occur in systems of spins, in cold atomic gases, and trapped ions, quantum fields, even quantum gravity. And there are actually different interesting cases. So I talked so far about the case where the interactions were few body and local. But actually it's also quite interesting to study the case where the interactions are few body but non-local. This is actually relevant for the case of black holes. And some of the reasons why we're interested in this physics, there's been suggestions, for example, that scrambling, that is the spread of information, because information sort of is the fastest thing in a system, maybe it could give you bounds on transport. Sort of the motion of conserved charges must be slower than the motion of information. And so maybe this butterfly effect, this sort of quantum butterfly effect, could tell you something about how fast charge could spread or energy. That's one idea that's been pursued by Sean Hartnell, Mike Blake, and others. As I already argued to you, it looks like it's an interesting diagnostic of many-body quantum chaos, something we didn't have a lot of good handle on previously, I would say. It can also be related to the growth of entanglement in a quench. And actually, it's also related to the emergence of locality and causality in quantum gravity. So this is,
Brian,
yes.
looking aside semantics, is scrambling saying much more than how time-dependent correlation functions vary as a function of time in non-integrable systems?
How time?
Dependent correlation,
Yeah.
I take some operators, I can define any kind of correlation function I want, and in a non-integrable system, they'll decay in some manner if I could calculate it.
Yeah.
And so I'll start with something and it'll disappear.
I would say two things in response to that. First, as I showed, it can be measured by such correlation functions. The only important physical point is that correlation functions are sort of qualitatively different than the kind we normally think about, and they expose a different time scale in the dynamics. And the other thing is it's not, not all such correlation functions have a nice information theoretic interpretation, have these nice features, of bounds and so forth. And so there's another reason to consider this special class.
So there are specific classes of them which have some significance.
That's right, that's right.
Your last bullet there
Yes.
seems rather innocent, but it seems to be packed with all kinds of possibilities. Would you say a little bit more about it?
I will actually show you a slide in a second. You willing to wait a few minutes?
Sure.
So what I want to do is talk briefly about one aspect of this physics, which is the idea of emergent speed limits. And then at the end, I'll talk about the experiments that have been done so far and what the next steps are. So this person is experiencing an emergent speed limit. The density of interacting animals has increased substantially, and now they can't go very fast. So we like to explore this kind of physics in interacting quantum many-body systems. I mean, and the reason why I want strong interactions is because in the case of weak interactions, we know what happens. We have waves, they have some group velocity, and that's how things spread. So we sort of understand that physics. So I want to go to the opposite limit, where I don't have a nice sort of particle wave picture and ask about the rate of information propagation. And I'm going to use my out-of-time order correlators as a tool to probe this physics. So here's kind of the naive cartoon. I have this is like a trotterization of some quantum evolution. And there's a naive light cone, if you like, which is if I put information in here, well, it could go to this line, then it could be spread by this unitary to this line, then spread to there, then spread and spread and spread. Right? So in principle, the information here could end up over there. And so the worst case would be that this wave packet would move to this dotted position. However, it may be in some physical system that for some reason the packet moves much more slowly. Information propagates more slowly. And this out-of-time order correlator provides a way to diagnose that. So here's a simple way of understanding how that happens. This is a simple communication protocol. I have two parties, A and B, or Alice and Bob. So you imagine Alice controls some part of a shared quantum state psi, and she can encode a message with some operators x. They can either be x0 or x1, so she chooses two different operators to apply. Then there's some separation between Alice and Bob. Bob controls a different part of the same state. And Bob can make a measurement at some later time to try to extract the message that Alice sent. And you can do a little calculation, which is the probability that Bob measures B given that Alice did A, minus the probability that Bob measures B given that Alice did nothing. This is something proportional to the sort of ability to send information, right? If this is small, then Bob can't tell what Alice did. So we want this to be large. And so what you find after a little calculation is that this is a commutator here between Bob's operator and Alice's operator evolved in time. And so if you want to ask how information propagates, you could ask how big this commutator is. And so one thing you can say is, well, I can always bound this matrix element of the commutator in terms of the operator norm of the commutator. That's some state-independent bound, which applies for every possible quantum state. And that's called a Lieb-Robinson bound. And there's been a lot of work here, actually, in JQI, studying these kind of bounds in non-local models, both theoretically and experimentally. But you might say, well, state-independent bound is too strong. I don't want to know what happens in every possible state. The speed of sound depends on temperature. I don't care if at 1 million Kelvin the speed of sound is a lot faster. If I'm interested in information propagation at room temperature, then I should put that information about the state into my calculation. And so one way to do that is to use the out-of-time order correlator in the guise of the commutator. So there's a little mathematical manipulation you can do to show that the magnitude squared of this probability of messaging can be upper bounded by, you do a little simple math, upper bounded by the square commutator. So this is a state-dependent bound on the weight of information propagation, which really knows about the state that they share. Okay, so this is a kind of way to motivate the square commutator as a sort of information propagation measure. And the key physical quantity will be what we call the butterfly velocity. And the way to think about this is it's like I have my operator W. W as a function of time. At 0 time, it's localized, saying a single spin flip. But as a function of time, it grows, it expands, and is supported now over a more complicated set of spins. And it typically expands ballistically with some velocity, which we call the butterfly velocity. So this is the definition of the butterfly velocity. This is generic behavior for a chaotic interacting spin chain, see. And so the idea is that this commutator will be significantly non-zero if the distance between the operators W and V is smaller than this operator radius. So if it's smaller than the butterfly velocity times time, then the commutator will be non-zero. So now I'll just give you some examples of calculations we've done. So one calculation you can do, which is sort of like a weak coupling limit, is you can study an quantum field theory with ON symmetry. So ON is orthogonal group symmetry. So for example, think about a magnet with some three-dimensional rotational symmetry. That would be O3. So this is like a quantum phase transition between a magnetized phase and a paramagnetic phase where the spins fluctuate. And in the limit of large n, this theory is weakly coupled, and we could study it in perturbation theory. And in that case, we find that the particles are sort of weakly interacting, and actually that the butterfly velocity is essentially the same as the speed of light. So I've set the speed of light to 1 in these units. I emphasize this is not the physical speed of light. This is sort of the speed of light for this material system. And so that's kind of natural. You know, the speed of light in this relativistic quantum field theory is the absolute upper limit on any information propagation. And so in weak coupling limit, we find it's just the speed of light which controls everything. But we could consider a very different example, another very physical example, which is a metal in 3 dimensions with static disorder. So you have impurities throughout your metal, non-relativistic fermions at finite density, and with some interactions, Coulomb interaction or some short-range interaction. And we can do a calculation in that case in perturbation theory, but resummed in some interesting way. And we find there, in that case, that there's now a butterfly velocity, but which scales as temperature to the 3/4 power. So it's a funny scaling of temperature here. And the physics here is that in the non-interacting limit, the particles in this dirty metal diffuse. It's just diffusion, so everything moves diffusively. However, when you turn on interactions, although the charge must move diffusively, the information can now go much faster. So charge diffusion survives the turning on of interactions, but information propagation changes from being diffusive to ballistic.
That sounds remarkable.
I'm glad you think so.
Can you give us a little bit more motivation for how that magic happens?
Yeah, I mean, I think the idea is sort of like the particles are moving slowly, they're diffusing, but to transmit information doesn't require physical motion of charge. It only requires some, say, scattering of charges. So that scattering can happen in a way which is not limited by the charge motion. So if you like, there's sort of other degrees of freedom or other modes in the system that can carry information, and those are not restricted to move diffusively. So this cartoon here can give you another perspective on that. In this theory, we computed the spatial dependence of this commutator square, and what we found is something like this. So here is ordinary diffusion, the x squared over t. And that's what you'd get if you just looked at, say, the spread of charge. This is the current response. However, there's also this chaos physics. There's some exponential growth. That's encoded in the exponentially growing term. And now if you balance these two terms in the exponent, you find that what you get is not a slow spreading which goes like square root of time, but actually a ballistic growth, where the ballistic growth is proportional to the square root. The speed is the square root of this chaos exponent times the diffusion constant. And so that's actually what we find here, is that this butterfly velocity is the square root of the diffusion constant times a new time scale, which is the rate of growth of chaos. And so the physical picture is that you have these particles diffusing around, moving slowly, but they're kind of infecting each other with chaos. The chaos is spreading rapidly. And that rapid spread of chaos, that growth of chaos, that infection process, leads to effective ballistic growth, even though the charge is moving diffusively. Yeah.
So the first case, the charge and presumably charge and information transport happen at the same speed.
Yes.
But this order, it's slower. So is it generically true that it's slow? I guess it has to be slower.
It's definitely slower, but how much slower is depends on the system. So this is sort of interesting. This is what I would call an emergent speed limit. Things are moving. Like if you looked at the Lee-Robinson bound for this lattice system, such a bound exists if you have short-range interaction, and it would be some number of order 1 in lattice units. But here we're finding that actually information spreads very, very slowly at low temperature. In fact, it goes to 0 at 0 temperature. So that seems quite interesting. We can actually, yeah.
How do you fit into the old like tuning result? Because there's an explicit calculation of the power time molecule later, and it doesn't have this fall in just exponential growth, not something that's summating.
Yeah, and I think in their case, it's more like a single particle picture.
Yes.
So here I'm talking about and you're looking at the sort of particles in like a billiard, so to speak, or some disorder sort of arena. And here I have a slightly different picture in mind where I'm looking not at the momentum of a total particle, but at some localized sort of excitation which can spread. Right. So I think that they're compatible, but.
So if you looked at the full momentum of a system, would you expect it to be different?
The full momentum of a system. Yeah, I think in that case I would need to think more, because what's important here is I'm studying local operators. And in the case of the full momentum, the physics is quite different. So I wouldn't necessarily, and see, that's already spread over the entire system. So there's no notion of like spreading in space. It's already everywhere. So I think the physics in that case is interesting, but different from this physics here. Yeah.
Is there some sort of like notion of a continuity equation for this like information, like there is for charge, if charge density and charge current is locally conserved?
That's a good question. It looks like actually not. I mean, in the sense that you can kind of actually, if you look at this form, you can write down an equation which gives you this, which is like tanh derivative of this quantity is the gradient squared of it. That's like a diffusion equation, which looks like conservation, but there's also a growth term. So it's like diffusion plus growth. So it's actually not conserved. So it's a sort of different physics.
So, Brian,
Yeah.
at this point, the speed limit, for example, light being the highest, usually when we teach students, we say that it is material particle, which has this limit. Now, how do I think in terms of information now?
Well, information has to be carried by something, right? I mean, information is physical.
Right, but are you identifying, for example, that lambda LT as presumably someday we will find out is the speed of light for us?
Well, this lambda, I mean, this is a rate. It's a 1 over a time, so it's not, doesn't have the right units to be a speed.
Right.
But the combination of this with the diffusion constant has a speed, units of a speed squared.
Right, but then you would say that that actually is a speed governing physical entities.
Yes, it's this. I mean, if you could do this experiment that I showed you,
Yeah.
suppose you have however many years from now, you have a real quantum computer in your lab. You can do this experiment, and that will be the speed at which you can signal. It'll be this speed, this VB.
So you seem to say that it is identical to the speed of propagation of information.
That's right.
So we're drawing this distinction between the speed at which charge, or let's just generalize it and say material stuff moves, and the speed at which information moves. Yet we're taught as a kind of a mantra that information is physical. So how do they end up being separated?
Well, I'd say the right way to think about it is to distinguish things that are conserved and things that are not conserved. So conserved quantities, they move in the usual way that we're familiar with, like matter. Mass is conserved in, say, fluid dynamics. But information doesn't have to, it doesn't require you to move mass to spread information. This I can talk to you, and then you can talk to Balak, and Balak can go forward, and no one ever changed any mass.
Right, but we do exchange maybe at least photons.
Well, yeah, we
photons or
exchange.
something like
No, I completely agree with you. But like, let's say I send you a little message, and then you send him a little message, but you use different particles. So my particles are never getting very far, and yours are never getting very far, and nevertheless it continues.
So what you're saying is that it's sort of like, well, tell me if I'm right here, sort of like the idea that when we transmit sound, the molecules aren't moving, but
Yeah, it's a similar idea,
okay.
but in a sort of more difficult to comprehend, strongly interacting quantum many-body system. Okay, let me go on, if you don't, because I want to say a little bit about experiments. So you can do other calculations in ADS-CFT. You can also find interesting butterfly velocities that depend on temperature in fun ways. These are like strongly interacting conformal field theories. I promised to say something about quantum gravity, so here's my quantum gravity slide. This is ADS-CFT in half a slide. So here's the boundary. This is where the CFT lives. The gravity lives in some emergent direction. So this round direction is the emergent direction. You should think of it as being associated with energy scale or length scale in the CFT. So short distance phenomena occur near the boundary, long distance occur deep inside. And the way the butterfly velocity appears here is quite interesting. If you take a particle near the boundary and let it fall inward at the speed of light, and you ask, there's a precise notion in ADS-CFT, how big a region on the boundary do I need to describe the falling of this particle? So the farther in it goes, the bigger a region I need on the boundary. And if you ask, as this particle falls in with the speed of light in the bulk, how rapidly does this boundary region grow? It turns out it grows with the butterfly velocity. So if information propagated more rapidly on the boundary than the butterfly velocity, you'd find that actually things would move superluminally in the bulk. So this slowing down in a strongly interacting CFT is actually responsible for consistency of causality in the bulk gravity theory. Okay, this is just you can do a calculation, it's hard. I'm a real theorist. It's not just all pictures. This is a square commutator. This is like you can do an expansion with some vertex, blah, blah, blah. This is the first term. It grows linearly with time. You can resum them, do some diagrams. It's very complicated. It's real-time dynamics at finite temperature. It's quite interesting technically. And at the end of the day, you can back out a growth exponent, which is what I was showing you in the previous slides. Okay, let me talk about experiments in the last 12 minutes or so. So the interesting thing about experiments is that you seem to need a time machine. And we'll actually see that in a second. And actually, I learned that we're in luck because DeLorean is making new time machines. So they haven't delivered yet, but they're hoping for 2017, maybe Q4. So all you need is some kind of capacitor on here, and then you're good to go. All right. So let's talk about how you can actually measure this in the lab. This was one of my major interests getting into this field, was how to take these abstract theoretical ideas and use techniques from quantum control, from AMO physics, to actually design an experiment. And the simplest thing you can do is to sort of try to be just very literal about what this thing means. So let me interpret the out-of-time order correlator, F here again, as an overlap of two states. One state where I start with psi, I apply V, then I go forward, apply W, and go backwards. That's the Heisenberg operator. And another state where I do the W part first and then the V part. That's a literal interpretation of what that object is. And so in terms of experiment time, I sort of want to do an interferometer between two branches where I sort of do V, then W, then versus W, then V. And you can do that at the cost of adding one extra ancilla degree of freedom, which essentially controls the application of operator V. So I have a system now, and I have one extra ancilla, and depending on whether the ancilla is in 0 or 1, I either apply V before or after the application of W. That's, I think, a very straightforward idea. Here's a quantum circuit that encapsulates that protocol. I start with my state at any state I want. The ancilla is in the 0 state. I do a pi/2 pulse that puts it in 0 plus 1. Then I apply a control V operation. Go forward in time, go back. I apply W, I go backwards in time. Then I flip 0 and 1. That's a pi pulse. I do another control V, and I pi back and I measure in the x basis of this ancilla. And what you can easily convince yourself with a little bit of algebra is that the expectation value of the x component of the spin of this ancilla is just the real part of f. So it's directly the commutator. Now I'd like to mention, this is sort of, it's a nice protocol, but it's a straightforward one. There's actually a lot of other ideas, some of which I've been involved with to measure this thing. One by people here at JQI is quantum clock. So in this protocol, you actually let the ancilla control the direction of time as well, and this can remove some sources of systematic error. There's also what's called a purity-like measurement. It's like measuring a Renyi entropy. And the nice thing here is that you don't require time reversal, but you have to have 2 copies, and the signal's exponentially small, so there's the usual trade-offs. There's another idea that was sort of pioneered by Nicole Younger-Halperin, which then I helped a little bit on, which we use weak measurements. The nice thing here is that the ancilla don't have to be coherent. And there's a decoding approach by Benny Yoshida, and actually many other proposals. So this is a very interesting and active area. Let me just give you one example of a system that my colleague at Stanford and I cooked up. So actually, this is the system that Monica Schleyer-Smith is building in her lab at Stanford. And we discussed for a while and came up with this sort of scheme where you could measure these time order correlators in an interesting chaotic system. Just to give you a sense, I'll go through this very quickly. You may have an optical cavity, for example, with some mirrors and a laser beam and some optical field in the center. And you have an ensemble of spins and maybe a control spin that's off to the side. And you control this via laser fields that are addressed via the side of the cavity. And the idea is these atoms are three-level atoms. They have some sort of up-down state, which we think of like the low energy states, and some excited state, which is much higher energy. And using a combination of the cavity coupling, which is G, and these control fields, which are omega up and omega down, we can drive certain transition pattern with some detunings. And the net result is you get an effective interaction when you sort of integrate out the excited states. You get an effective interaction, which looks like a spin-spin interaction. That's kind of the model I started with at the beginning of the talk. And depending on how the shape of these control fields, the mode structure of the cavity, and these detunings, you get certain Hamiltonian. Okay. And the nice thing about this Hamiltonian is that just by changing the sign of this detuning, little delta, this is the 2-photon detuning, you can actually adjust the sign of the entire Hamiltonian. This is the kind of thing we're interested in. We have sort of an interaction, and just by changing the detuning of one laser or some number of lasers, I'm a theorist, we can effectively reverse the sign of this interaction. If we combine this with some fields that we can apply, field in different directions, well, then we have essentially the model that I talked about on the first slide, modulo this spatial structure here. Okay, so I want to skip ahead a little bit. You can benchmark this in a simple limit where you have globally interacting spin, so every spin interacts with every other spin. You can design a chaotic Hamiltonian, or actually it's a sort of Floquet system where you're doing 2 different things in a pulsed sequence. So you do a spin rotation and a sort of SX squared. This is the interaction part. This particular unitary is known as the kicked top. It's been studied a lot in the literature as a simple example of a quantum chaotic system. And the key feature here is that you've reduced everything to the symmetric subspace. So all you have n atoms, the Hilbert space size is not 2 to the n, but just n, because you're in the symmetric subspace where all of the states are symmetrized. Okay, the model is chaotic classically, and then you can look at, say, you can simulate what you would see if you did an experiment with different numbers of atoms, 50 to 500 from lighter to darker. And this G is, say, some ordinary time-ordered correlation function, so just like an autocorrelation function here. And you see it decays. If anything, it decays more rapidly as you make the system bigger. But the out-of-time order correlator decays more slowly as you make the system bigger. And that's probing this fact that the bigger the system, the longer it takes to scramble. Right? So this is sort of the simplest version in this kicked top model of the growth of scrambling. And the increase of this time scale scales in some way with system size approximately logarithmically. So that's one example. Now, with that in mind, let me talk about the experiments that have been done so far. So the first experiment is an experiment in trapped ion, two-dimensional penning trap, a beryllium if I remember right. They had about 100 spins, which is nice. That's a big number. But they were restricted to this symmetric subspace. So the Hamiltonian they implemented was just the SZ squared Hamiltonian. This was by coupling the spins to some collective mode of the trap. And so this is neither chaotic nor many-body. So it's nice as a first step, but we're not probing, I can easily simulate this, just a 100 by 100 matrix on my computer. So I'm not yet learning about many-body chaos here.
So what was the point?
Well, the point is that it's complicated an experiment to do. There are lots of sources of error. And so essentially they're trying to take steps to sort of understand how decoherence affects the physics and this kind of thing.
So setting up
It's sort of a setting up, yeah, I would say. There's an NMR experiment that followed, probably happened at the same time basically, which they in principle have an interesting Hamiltonian. It's this sort of SZ, SZ, SX, SZ that I showed you, but it's only 4 spins. So again, they're working towards it, but we're not yet learning anything about many-body chaos. Now, more recently, there's another NMR experiment with spin chains. Actually, they had about 40 mini chains of like 40 atoms each. They had a very complicated Hamiltonian. This is an experiment in Paolo Capollaro's group at MIT. Very complicated Hamiltonian, including disorder. So these H's, these fields can depend on position. And what they actually explored was localization physics. And they couldn't resolve, it's NMR, so they didn't have resolution at single sites, but they did measure some interesting things about the growth of operators. And there was another very recent experiment in which they used BECs, actually momentum states of a BEC, to realize this kicked top again, but they're only like 5 states, so still not, it's sort of setting up the stage. Just to give you an example of the data, let me focus on this Capollaro experiment. So here, this is the actual data. They started with a state which is identity plus a small amount of total SZ. So identity plus epsilon times the sum of all of the Z operators. And they essentially measure how complicated this Z operator grows as a function of time. How many poly operators appear in this time evolution. And so this is time, milliseconds. This is the correlation length, which is what they call just the average size of the operator. So in other words, the operator starts out as a single site operator. As a function of time, it becomes complicated. It expands. It encodes more poly operators. And we're asking how many, on average, poly operators appear in that expansion. And what you see is, this is as a function of interaction strength. For 0 interaction strength, the operator grows a little bit, but then saturates and stops growing. And this is supposed to be a picture of Anderson localization, where everything stays exponentially localized in space.
So there is disorder in this.
There's disorder, that's right.
But the theory had no disorder, right?
Which theory?
All the theory that you talked about.
No, the metal had disorder.
No, the metal did, but the numerics that you showed.
The numerics I showed.
Changed the physics quite a bit, right?
The disorder would change the physics quite a bit, that's right. In fact, I didn't put it here. Banjan and I have a paper on this physics in many-body localized states. But anyway, so what you see when you turn on interaction is that this is time on a log scale. You see that there's some growth, and then it looks like maybe roughly the operator is growing logarithmically with time. And that's actually what you expect in a many-body localized state. So maybe this is the first inklings of some interesting dynamics of operators in an interacting system. That's that. So that's the state of the art.
But I'm confused.
Yeah.
What is different other than it's being done in this context of OTOC compared with what huge number of simulation people have done in the
No, at the level of simulation,
yeah.
it's not really different. I mean, they have 40 spins,
But
so
even in the experiment, it's just doing the same thing and calling it something else.
I wouldn't go that far, maybe, but I agree we're not really at the point yet where we're learning something we didn't really know.
The point is that we do many-body localization. Shaoli can give you OTOC today. He has,
Yeah.
So what exactly is the progress is I'm trying to understand. Usually semantics doesn't induce progress in physics, but maybe it does. Maybe I'm wrong. Okay?
Well,
Maybe
it
just, taking the same
might.
thing, putting new clothes gives you something?
It might actually, but the message here I think is that we're not done yet. I mean, we've just started. We're just learning how to do these experiments, and we actually haven't really, in my opinion,
Framing the questions.
we're still sort of setting things up, understanding how to do the experiment, how to correct for decoherence and all this sort of stuff, and we're not there yet in sort of seeing really novel physics of many-body chaos we can't access, on my Surface Pro here.
So, question on
Yeah.
the left to the right. So there's sort of lots of wiggles there, and presumably we're looking for some linear regime. But is that easy to tell from?
No, I mean this is a simulation first of all,
Yeah.
and this is entropy as a function of time. So this is supposed to be this log growth.
So
But-
there's no apparent function in there.
Yeah, I don't know what's going on there. Ask them. I should have blanked that out. Only look at this one. Okay, so in the last negative 1 minute, I'll just mention that you can think about the effects of imperfections, and I'll show one fun plot, and then I'll stop. So you could ask, well, what happens if I reverse time forward and backwards? That's what I'm asking you to do, but what if I make a mistake on the forward part and the backward part? I'm surely going to do that, right? I can't adjust the dials perfectly on my oscilloscope or whatever. So what happens if I make that mistake? And so what I do is I took this this parallelizing Hamiltonian, and I add a random z field and a random zz coupling on the forward and a different one on the back. And now this blue curve is the ideal. It's the straight line again. The red is the error. So that's if I do the protocol without doing anything else. And you see it looks bad. It's totally different. The slope is different. The magnitude is way different. But what we found is that there's a way to, by dividing two experimentally measurable quantities, taking this ratio here, or either apply the operator V or don't apply the operator V, it's possible to actually remove effectively a lot of this noise and return much more closely to the ideal curve. So this renormalization formula, which is itself an interesting theoretical artifact, may help us do experiments on bigger systems where these kind of imperfections would otherwise really kill us. We can actually get quite close. And I emphasize this is on the log scale, so this should really impress you because it's really close.
Yeah, but what my experience has been, interacting closely with Emmanuel Bloch and Chris Monroe,
Yeah.
is that experiment can do very large system, indeed true, much larger than what I can.
Yes.
But it comes to time, the experiment cannot do anything. In time, the finite time limitation in experiment is severe.
Yes,
So making any statement about the saturation, entanglement, entropy, any question,
Yeah.
time is 100 in units or anything,
This is
they have no
This is a great point. So in fact, at the present state, we have no hope of observing this long-term thing. What we could hope to see is maybe the growth.
So
Maybe.
You better look for quantities which are basically transient, very short time.
Yeah, that's
what
this,
experiment can do very
for example, this growth phenomenon, I think something we could hope to see.
But the time is only 8, right? So that doesn't look like a long time.
Yeah, this is only 8j, 8 over j.
This is simulation.
Yeah.
But they should be able to get to 8.
Okay, let me summarize and stop. Okay, so
Most go to just like 2 or 3.
So what I showed you is we have new tools to understand the spread of information. Among some of the things we discovered is that we have slow speed limits in some systems. It's related to quantum gravity in an interesting way. There are a lot of questions, and I think hopefully in the coming years we're really going to see some experiments that push us beyond what we can do on our computers. And this can come from a variety of directions. Okay. And the final thing I'll say is if you thought this was interesting in any way, come to my group meeting, which happens on Thursdays from 5 to 6 in PSC 3150. All right. Thank you.
Just to clarify what you said, I things that Lieb and Robinson found